we can start today. We have a guest from the University of Leeds, Dr. McQuaid. He is going to give us two talks with break. First one will be Geoengineering the Climate. So, Jim, the floor is yours.
Okay, thank you very much. This is my final stop on my tour. I've been to Krakow, Budapest, Veszprém, and Bucharest, and finally Zagreb. So it's very interesting to see across Eastern Europe. I didn't realise that Romania and Hungary were in two different time zones, which was interesting one morning. So just one thing to point out, and I've been asked to do this by the Office of the European Association for Geochemistry, but they do have money for, particularly for PhD students, to attend conferences and things like that. So do think about that. As with everything in this world, there is a website that you can go to for more information. So this afternoon I'm going to give you two talks, and there's quite a lot of overlap between them. So they do tie in together. But I'm going to start off talking about geoengineering the climate, and exactly what do we mean by geoengineering the climate. Some people say we've been geoengineering the climate since we first lit a fire. That was the first thing we ever did, in planting crops and chopping down trees and things like that. So, but I'm going to start off with, and this normally gets people's attentions, especially undergraduate students, just to put that up there, and I'll come back to it. And I use Guinness as a teaching aid about aerosols and physics, and particularly this. So we'll come back to that. But just start thinking about that, because people will remember that. The person who started off a lecture by talking about Guinness, and I don't think there's many people who actually do that. But before I start off with that, because these talks are sort of sponsored by the European Association of Geochemistry, and I'm not a geochemist. So the first thing I've done when I've been talking to geochemists, because they want to know why an atmospheric scientist is talking to geochemists or geophysicists. But it's because I work with geochemists, and after this I'm going to the synchrotron just outside Paris to work looking at some of the samples we collected in Greenland last year. And that's very much a mixing of atmospheric science, geochemistry, microbiology. So it's a nice example that just demonstrates that we're not just in one area of science. We should look outside and talk to people, talk to other people, sit down, have a cup of coffee, and just see where there are overlaps. So I did actually do, a long time ago, I did a chemistry degree. And then between the chemistry degree and going back for a master's, I had like a 4-year break while I thought about what I wanted to do. And I ended up working for a band. So I was the road manager for a band. And this is, we were the support band for another band you might have heard of. You won't have heard of the Utah Saints, but you'll have heard of U2. So this is the Lisbon Atletico football stadium, 70,000 people waiting for U2, but this is us coming up. And that's the top of my head. So I wasn't in the band, I'm not a musician, but I set up equipment. And so why do I mention that? Because setting up this equipment is just like doing field work. Because this equipment sits in a studio, field equipment sits in a laboratory, it's electronics. You take it down, you put it in a box, you put it in a lorry, you send it somewhere, you get on an aeroplane, you go to where the lorry is, you take the equipment out, you set it up, you plug it in, you pray that it's going to work, and it either makes a measurement or makes a noise. That's the only difference. It's exactly the same thing. So, and 70,000 people stood in front of you. So, so I had that experience, and that proved very helpful when I went back to start doing field work. So I went back and I did it. So physical chemistry, looking at reaction kinetics. This is atmospheric chemistry. I made a smog chamber, so a Teflon bag that I did chemical reactions in. And then I went to do a PhD, and I did this sort of thing, but in the atmosphere, looking at the transport of pollution. And that was on the ground, and then I started working with aircraft. So this is the first aircraft I worked with. We used to have a Hercules aircraft in the UK. And if you notice, there's people here, they've got sunglasses on. And that's because we did a chemistry experiment using solar eclipse. Because with the solar eclipse, you fly out and suddenly you turn the light off. So you suddenly stop the photochemistry. It's a very difficult thing to do because the sun, we don't have control over the sun, but you can do that. So that's what we did here. Working with an aircraft like that, flying suits, so everybody gets a chance to take their Top Gun photograph. I think everybody who ever worked with the aircraft has got that. So I've worked with a number of different aircrafts. This is one I'm in this aircraft, 400 feet, so that's about 120 metres above the Swedish icebreaker Odin, and we're about 80 kilometres south of the North Pole there.
Where did you do your PhD?
In Leeds. So I was born in Sheffield, and I went 50 kilometres up the road in 1987 to Leeds, and I've never left. So not very adventurous. I do a lot of field work, but I always go back. So yeah, so Sheffield, Leeds, 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 Leeds. Not the standard profile, which, you know, a lot of people go to all sorts of different locations, but I was happy in Leeds. I met my wife in Leeds. She lives in Leeds.
You know some people in Leeds?
I probably know quite a lot of people that you know, with geomagnetics and John Mound, people like that.
Ian Brooks.
Ian Brooks is in the office next door to me.
All right.
So, actually, Ian Brooks was on that ship. How small's the world? And his wife was on the aircraft with them. Barbara was on the aircraft. That's the closest they got in 3 months. Okay, 400 feet. It's not very far. Not very far. But it might as well be 1,000,000 miles if you're so. There you go. I don't think we can get any. Does anybody know my next door neighbour, my wife? Yeah, but you know, Ian Brooks. So
I should stop.
So, and then from this aircraft we moved to another aircraft. It's about the same size. But it's used as generally a city jet. Takes about 120 passengers. But we take all the seats out of it. We put instrument racks inside it. And because of doing this, I put lots of instruments on the aircraft. I got a phone call about 6 years ago now from the BBC, and they had hired an airship, a Zeppelin. So this is 80 metres long. They were going to fly across America in it, and they were going to measure clouds. They called it the Cloud Lab. And they said, well, we want to do some experiments. So I helped them with some experiments. And then they said, do you want to come along? And so this is a difficult question. Do I want to go on an airship across America for a month, possibly flying over the Grand Canyon? So that was quite a difficult decision, so I did that. But that's, again, it's all a lot of the same sorts of things. If you're on field work, something's broken, you suddenly have to fix it. And it's what you've got in your pockets. And then finally, the work I'm doing on most recently, this is where the samples, they're actually in my case that I'm taking tomorrow. So this is a huge interdisciplinary project. This is one of these big projects where people from lots of different areas come together. So this is our project. It's called Black and Blue. This is the Greenland ice sheet. The Greenland ice sheet is not as pristine and white as you may think. This is deposits from the atmosphere landing on the snow, and also algae growing on the snow, changing the colour of the snow, changing the melting rates. And this is the culmination of lots of different people going to Greenland and Iceland and places like that and measuring different parts of the same story. And then finally they all sit down and they go, we should all go to the same place at the same time and measure all our different things and put that jigsaw together. So that's what we're trying to do with that. But that's my potted history where I'm coming from. So geoengineering, as I said, the definition these days is the deliberate large-scale intervention of the Earth's natural systems to counteract climate change. Some people don't believe in climate change. Mr. Trump isn't very keen on it, but I think generally the rest of us are. So as I said, and one question that people have asked is, but haven't we been geoengineering the climate since we first chopped down a tree, started domesticating animals, lit a fire? So, but now traditionally, geoengineering is sort of our solution to climate change. Maybe solution is not the correct word. So, and a lot of this information is taken out of a report put together by the UK Royal Society. You can download this, it's very easy to find, loads and loads of information, and this is very accessible. It was written so it can be understood by politicians, not scientists. There is a big difference. So, and that's nearly 10 years old. There's a lot of interest in geoengineering, whether it's a good or a bad thing. So, just to start off with some fairly basic energy statistics. So, despite what some people think about how the energy exists on the planet, whether it's all coming from geothermal, there are some people who suggest that people generate all the heat, and it's nothing to do with the sun, but it doesn't take long to work out that the sun is the source of all of our energy. So there's a lot of it comes down, it's absorbed by the surface, some of it's reflected out on clouds, reflected out by the surface heats up, it radiates out infrared, longer wave, thermal energy, and then that's absorbed by greenhouse gases, clouds, so not all of it goes back out to space. So, and the more we stop it from going out to space, that is global warming. So, and the two main approaches to geoengineering, so there's the system that allows the atmosphere to warm, and there's lots of greenhouse gases, but we're just considering carbon dioxide here, but there are lots of other greenhouse gases. So can we control the amount of carbon dioxide in the atmosphere? If you reduce the amount of carbon dioxide, more of the infrared radiation gets out, doesn't get trapped by the carbon dioxide. Or do you stop the sunlight from getting in the first place? Do you put an umbrella or a parasol? So this is solar radiation management. And there's some concepts that, so how many people are comfortable with the idea of albedo? How many people have heard of the word albedo? Oh. Good. Right, okay. So that means some of these slides we're just going through, as you know. But a lot of people, the thing about albedo is it's a word that, you know what it means, and lots of people, other people know what it means, but they've never heard of the word. So it's a word that we use, and people are comfortable with, black things absorb more sunlight and warm up, but they don't know the word albedo. So this is the main figure that I expect in a PhD dissertation if someone's talking about climate thing. You show them this, and where do you fit in this? Everybody fits in here. It's talks about atmospheric chemistry, primary. These sorts of compounds react to produce these ones. So you can see they're all tied in. Then we've got aerosols, things like mineral dust, which I'll talk about later on, clouds, black carbon, all these sorts of things, how they interact with clouds. We're changing, there's an effect from just land use change, chopping down trees will change the colour of the land. So this is the main line we think about. Anything in that direction warms the climate, anything in this direction cools the climate. And the important things are these uncertainty bars, and the bigger the uncertainty, the more we need to know about them, the less we understand about them. And that's why if you look here, this is where there's an awful lot of research goes on at the moment, understanding about aerosols in the atmosphere. Because carbon dioxide, those sorts of systems, we've known about carbon dioxide for a couple of 100 years. The people have known that, so that's quite well known. There's a reasonable uncertainty there because it's how these things feed into that. It's not actually, we know carbon dioxide absorbs infrared radiation. That's That is something we really do know. So we've got geoengineering, thinking about how we're going to deal with carbon dioxide, or thinking about albedo, solar radiation management. And as we've seen, this is just accumulated carbon dioxide, reaching this magical 400 parts per billion mark. And this is the temperature anomaly. So that's the temperature that the atmosphere has increased by since pre-industrial times. That's our metric. So, and another magical number, because it's a number that people can think about, it's 1 degree. People don't think that 1 degree is a huge increase in temperature, but if you think about the entire planet, that's a lot of energy going into the system. And if you warm up the atmosphere by 1 degree, you can put 7% more water vapour into the atmosphere. Again, 7% doesn't sound like a huge amount, but when you're talking about flooding and things like that, and also crops, fertilising the crops, providing moisture for the crops to grow, 7% is the difference between crops, yield increasing by as much as 20%. So that 7% doesn't sound like much, but it is a lot, because it has a big knock-on. So just returning to that, so solar radiation management sits there, carbon dioxide removal sits there. So, and breaking this down, we have different approaches to the carbon dioxide removal. We can terrestrial biological systems, that's just fancy words, clever word for planting trees, things like that. So that's what goes in the report, and then you just say to a politician, plant trees. Oceanic biological systems, that's things like promoting the growth of phytoplankton that absorbs carbon dioxide from the atmosphere. There's all sorts of other implications for that. The main thing is it's removing carbon dioxide from the atmosphere by simply growing. And then they go into the food chain, and this material also falls to the surface of the ocean, deep ocean, where it goes into long-term storage. And then you can use what's called engineering solutions. That's planting crops and maybe burying the crops, sequestrating the carbon underneath the ground. And then solar radiation management, you can think about the atmosphere or the planet, and the atmosphere is different levels. So geo is the approach at the surface, so land or ocean albedo modification. Into the troposphere, so the troposphere is from the ground up to the tropopause, so the first 15 kilometres or so. The upper atmosphere, the stratosphere, all the way up to the mesosphere, and even space-based. So some people have suggested that we send reflectors out into space between the Earth and the Sun, which is a nice idea, but if you get it wrong, it's all going to go very wrong. So we can turn this into quite a nice diagram, sort of with a cartoon that shows a lot of these, so all the different approaches we can take and where they happen in the atmosphere. So planting trees, burying carbon dioxide underground, lots of different things, and not forgetting that 70% of the planet is covered with water, so can we use that. So I'm just going to take a few tables out of that report. So the carbon dioxide removal methods, the biological is planting trees, things like that. Fertilising the oceans. So the oceans around the globe, a lot of them are limited in various nutrients. It's not always the same nutrients. So some places are iron limited, some places are phosphorus limited, some places are nitrogen limited. So you'd think about how you're going to change that. Physically, can you just scrub carbon dioxide out of the atmosphere, turn it into calcium carbonate, bury it in the ground, things like that? Well, a lot of these, you've got to think, that's a nice idea, but you've got to build a big factory to do this, and how much carbon dioxide can you take out of the ground, or take out of the air feasibly? The various chemical approaches that we can apply to this, but they start getting quite expensive. You can grind up olivine and put it in the oceans, which actually makes the ocean slightly more acidic, alkaline, but that can be balanced out because they're absorbing more carbon dioxide at the same time. So, but that's a very fine balance, because you don't have to change the acidity or the pH of oceans by very much to start killing coral and things like that. Ocean acidification is not like a change in pH of 1, it's 0.01 to affect coral and things like that. So drilling down into this is looking at land use and afforestation. So what they've done is then they've broken it down to effectiveness, how good is it? Affordability, you've got to sell this to politicians. You know, do they want to prepared to provide the money from that? Because inevitably this thing means increasing taxes, and then politicians don't get re-elected. Politicians work on a timeline of 5 years, because they're not thinking beyond that, because they just want to get re-elected. So they don't want anything that's unpopular certainly towards the end of their tenure before an election, because they won't get elected. That's how politicians work. So there's timeliness. So just how quickly is it to switch? Do you put this in place and suddenly it takes has an effect? So if you're planting trees, for example, you can plant them quickly. It's not difficult to plant trees. You know, there's lots of school projects around the world where the kids go out and plant trees, but they have to start growing. So there is a lag time there. Some people don't like the idea of cutting down old trees and planting new trees, but old trees have stopped absorbing carbon dioxide. That's one thing to remember. So chopping down a big old tree that everybody played around when they were kids, from a climate perspective, it's probably more productive to take that tree out, as long as you don't burn it. If you burn it, you just put that carbon dioxide back into the air. But if you plant new trees, they suddenly start taking carbon dioxide out of the atmosphere. And then there's a safety consideration. So you've got to think about it, because this report tried to think about this very holistically. So if you plant lots of trees, what happens to the crops that you might have previously grown on that land? If you can't plant the crops, you have to get the crops from somewhere else, another country. So then maybe you've got all the carbon dioxide being produced, moving the crops back into your country, for example. But it may be that you spend so much time and effort making crops grow locally, it's more cost effective from a climate perspective to grow them in a distant country where they don't need as much fertiliser and artificial heating and things like that, than actually having them in glass houses growing in a colder country. So that's one issue. In the UK, a lot of people don't like the idea of importing vegetables from Africa, but actually if you look at it, you spend so much more energy forcing these crops to grow in the UK, whereas they naturally would grow better in Africa. So they produce less, well, there's less carbon dioxide in the whole cycle than being grown in Africa and then shipped over. So you have to think about all these. It's not just one thing, you've got to think about the whole picture with these, and that's what this report has tried to do. So we can remove a lot of carbon dioxide by growing vegetation. And the important thing to do, I mean, it's good even if we grow crops and use them as biofuels, at least compared to fossil fuels, because fossil fuels is carbon dioxide that used to be in the atmosphere that got buried away for a long time. At least if you're growing crops and then burning them, you're just cycling through the carbon dioxide in a time scale, depending on how long these have been grown, between 10 and 50 years. So that's one way of thinking about it. Just planting trees where it's been deforested, just plant the trees and leave them to get on with it. But then you can start thinking about, is there a way of capturing the carbon dioxide from the atmosphere and then using it as an organic fertiliser known as biochar, which is basically people grow crops, they produce charcoal, but they don't use the charcoal as a fuel, they use it as a fertiliser. Obviously there's only a limited amount of that you can use. You can't just continue to do that, because how much of this charcoal can you put into the ground? So there's all these different factors to consider, and they're not the factors. There are different weights applied to them depending on where you are on the planet. To think about it, it may be much more productive to do it in a developing country than it is in the UK or Europe, for example. So again, this other table, and there's just a couple of things to think about. Quite often with these, all these ideas of growing vegetation to remove the carbon dioxide, one of the big conflicts is food. People are saying you're planting these trees so we can use them as fuel or bury them in the ground, and you can't plant crops. So the local agricultural community is in danger. They don't like that. People get upset because they're thinking about food miles, food being imported, but that may actually not be such a bad thing. And wars for thousands of years have been about land, people reclaiming land of each other. So land use conflicts very quickly escalate. So they keep appearing in this table. So just to go back to this cartoon, so we've looked at these ones, so planting trees, burying it in the ground, thinking about can we put the carbon dioxide deep into the ground, capture and sequestration. And then let's go out. So the land, one thing about the land is it's reasonably accessible. You can walk to these places. If you start going out onto the oceans, that then gets, the complexity goes up an order of magnitude. Can we put this stuff into the ocean to fertilise the ocean, to produce phytoplankton, and the phytoplankton in growing, embarking on the food chain, will absorb carbon dioxide into from the atmosphere. So there's a number of different factors that we have to think about. How actually effective is it? One big problem is once you've changed the ecosystem of the ocean, it's very difficult to get it back. This is one thing. The human race is fantastic at coming up with a solution, and then 100 years later we realise it was the wrong solution. So you all know about Albedo, but has anybody heard of Thomas Midgley? So Thomas Midgley, 110 years ago, invented CFCs. Fantastic, non-flammable, anaesthetic gases, very stable, a wonder chemical, a bit like plastics. When people invented plastics are going to save the world. Now we think otherwise. He was also the same person who put lead in petrol. So one person, CFCs and lead in petrol. That's incredible. Okay, because motor industry getting rid of the knock in internal combustion engines, making the internal combustion engine run more smoothly. They don't break down. Fantastic. And then 80 years later, lead and brain damage in children and things like that. But that wasn't perceived. So the human race, there's just a couple of examples. The human race is fantastically good at coming up with these solutions, but then some long way down the line, we suddenly realise that there are good aspects and bad aspects to things. So if you start changing the ecosystem in the oceans, if there is some intended consequence, it's very difficult to recover from that, because the oceans, they talk to each other. The ocean circulation, it's very difficult to close that off. It's quite a slow process to have a large signal, but I think the biggest concern is this unintended consequences. People are now very, very reluctant to start doing big-scale experiments. There have been very short-term experiments, just putting iron filings into the ocean, and they've seen these phytoplankton blooms, but there's still a lot of reluctance to do this on a big scale. So we've looked at the top one, so dealing with carbon dioxide. That's taking carbon dioxide out of the atmosphere. Now going to solar radiation management. So a lot of this should be reasonably straightforward to a room of people that all understand the word albedo, which is always good. So albedo, there you go. So we're happy with that concept. So just to put, got a table. So even there's a significant difference between fresh asphalt and old asphalt. Ocean ice, fresh snow, you know, these sorts of things. You don't really get to an albedo of 1. So that's a difficult thing to do. I guess it's just like you know, people when they come up with the blackest black paint, it's still almost completely black, but not always. Things like, to bear in mind, bare soil, but bare soil, is that wet or dry soil? Wet soil is a lot darker than dry soil, but quite quickly if the sun shines on it, it dries out, but it drives humidity into the atmosphere, so you can see it's quite a complex system. And then just putting this into this figure here, I've also got, included in this, clouds. So clouds have a huge range in their albedo, and that's dependent on the density of the clouds, the size of the cloud droplets, and where they are in the atmosphere as well. So this is from the concrete promotion website. So I never knew there was such a thing, but they are just simply showing that tarmac, the difference between the albedo of tarmac and concrete, which is all well and good, but 5% of all carbon dioxide comes from concrete manufacture. So you can't just say we'll stop producing this stuff and produce this stuff. So there's no instant solution, a switch to this. And also, just to point out that the darker surfaces and the fact that in the urban environment, you know, these surfaces all have a big thermal mass. So this is the idea of what we call an urban heat island. So ignore the Fahrenheit, so just for the Americans. So this is the real temperature scale we should look at. And you can see, and actually it's not like this today, but a couple of weeks ago when I was in Hungary, there was a considerable difference between that, and people were saying it was about 4 degrees cooler out at the campus, because the campus is out of town. So, and this is simply driven by the fact that the albedo is different here, and also there's a much larger thermal mass. And this is significant enough to drive weather patterns in a lot of cities. Phoenix in the States is one of them, where basically the rainfall patterns have changed as the urban and the downtown regions have grown. So we can actually see that on the timescales where people can remember in people's time frames. So there are, the first solution when you explain to someone about albedo is to go, oh well, paint everything white. Which seems a great idea. But if you think about the planetary surface, painting things white, you have to paint an awful lot of them, because even the cities, think about the footprint of the planet, the cities are still a very small area. That said, in an urban environment, if you can cool the local environment by maybe 1 degree, that can make things a lot more comfortable for people. And in this day and age, not so much in the UK, but a lot of other countries, I'm guessing in Croatia, a lot of people have air conditioning in their houses. So the energy cycle, the seasonal energy cycle for a domestic environment is heating, and then it cools, and then your energy consumption goes down in the spring, and then as it gets hot in the summer, everybody turns their air conditioning on. So if you can reduce that, when people turn their air conditioning on, by maybe 10%, reduce that, that can have an effect. So there is, you know, a sort of domestic effect. There's a knock-on. In the same way, in the old days when I was young, when it was cold, we didn't turn the central heating up. You just put a jacket on. Simple solution. So a lot of these are, you know, so people think about changing colours of road surfaces, but you can't. It's not particularly sensible to do that retrospectively, but maybe when you're designing buildings, you encourage people to have lighter surfaces on the roof. People traditionally used to use bitumen and asphalt on the roof because it's a great material that's very easy to make a watertight seal on the top to protect against the weather, but it's a very dark surface. So think about new solutions for that, so you may be thinking about that in the future. There have been some modelling experiments, so a lot of the experiments with geoengineering are theoretical, people putting these into numerical models and seeing what happens. And if you change the albedo of crops, not actually by much, there is a potential to change to cool, and that's looking at North America and Central Europe by up to 1 degree. Again, the knock-on for the global temperature of that, there's probably an order of magnitude difference there. But then you've got the competition for, you've got to make sure these crops are pest resistant and things like that. So it's not as simple an idea as that, but there's certainly these are certainly the sorts of things that people are looking at. And then there's some slightly crazy ideas, possibly developed through a conversation around Guinness, where people go, we'll put mirrors all over deserts and things like that, but you take them out to deserts, sand blows over them and things like that. So, and against deserts, or even the Sahara, which is a huge expanse, is quite a small component of the planetary surface. So although they seem good, actually how big an effect they are is always worth thinking about. But like I said, we do a lot of our experiments using computers, and then every so often the planet gives us a helping hand to understand these things. And this is a great example is Pinatubo in 1991, also El Chichon in Chile in 1982. These were in the era of where we had good measurements, so we could track these plumes around the world. We could see how high they got up in the atmosphere, so we could look at the effect they had on the planet itself. And we can use that to test our models. It's very difficult to test models against some sort of global catastrophe or happening unless it actually does happen. So this is basically just a general circulation model, and these are the temperatures. So the temperature after Pinatubo went down, and that was tracked. And the good thing about that is, because there's so many different factors controlling the temperature, you need a big thing to make this happen. Pinatubo was indeed that big happening, and so we can see the solid black line is the temperature, and then we can see that the computer models, when we put these Pinatubo into the computer models, the amount of material thrown up into the atmosphere, the computer models were fairly good. That's 1991.
So is this average temperature or which temperature?
This is global temperature.
Global temperature.
Yeah. So and they put in things like the ENSO circulation. Yeah, this is a general circulation model. So this is a climate model, because the effect of Pinatubo was a global feature. And 1991, I'm guessing, is a little bit before most of the people in this room. And a great thing about having the two eruptions was, it's not, if you've got one result, that's great. If you've got two results that say a similar thing, that's not just better by a factor of 2. That's a square function. If you've got two things agreeing. So El Chichon, which is a smaller eruption, and you can see, so there's a smaller drop, and the recovery time was a bit quicker. But you've got the same sort of profile. Yeah. There's, these different features, if you can explain them, add to your understanding, your confidence in your climate models, how we understand how the climate responds to these sorts of things. So, and we could see this from satellites. These are, the quality of the data that we get from satellites now, is several orders of magnitude better. So it shows just how big an eruption these two were. And that's just showing sulfur dioxide. So that's from the TOMS satellite. That's also the same satellite that spotted the ozone hole, or confirmed the ozone hole. So we have this concept of not everything, we have lots of things warming the climate, but then we discovered that this drop in temperature, so we had global warming, but there's also global dimming. And it's just called dimming because all it was doing was increasing the albedo, the planetary albedo, reflecting some of the incoming solar radiation out, just dimming the amount of light that landed on the surface. And it happened about the same time as a lot of countries started trying to tackle sulfur dioxide, industrial sulfur dioxide. And this is generally because, and it was nothing to do, we didn't know about global, a few people thought about global dimming, but it wasn't the driving factor for this. It was because acid rain. So acid rain, particularly in the UK, we would burn high sulfur coal. The emissions, the sulfur dioxide would go up into the atmosphere, it would blow away. So in the UK, it gone. We didn't care about it. Until the trees started dying in Scandinavia, so then we and a lot of the other nations started to reduce the amount of sulfur dioxide being emitted out to the atmosphere. And it was because of acid rain, but we saw that had an effect of cooling the atmosphere. This was also confirmed by Pinatubo. So actually, in doing that, we increased the warming rate overall in the atmosphere. So now this is a movie, and this might work. So so we got to think about these things going into the atmosphere. So they have a direct effect on the albedo, they're there, but they also affect other things in the atmosphere, particularly things like clouds. So if you get clouds forming, just a different colour, so that can be an effect. So what we've got here is, and this is so this is a cup of tea, right? Nothing fancy, a cup of tea, right? I'm sure everybody in this room knows how to make a cup of tea, okay? Very easy science. So, and what's happening here, this is in the, on the side of an icebreaker, and a lot of people do this. It's a fairly standard experiment because you know it always is going to work. So we've got the pristine, clean air in the Arctic, and so this is the same temperature. We've got water vapour coming out of here, but it's not condensing because it has nothing to condense on. So until we add what we would call cloud condensation nuclei. That will run again. And this is our source of cloud condensation nuclei, aerosol. So the Zagreb provides cloud condensation nuclei. And at that point, that is the seed, the catalyst for water to start condensing onto. So you can see that this is where we come up with this idea of aerosol-cloud interactions. You can, by understanding the aerosols and the humidity and the temperature in a certain environment, you can have a go at predicting clouds. And if you can put clouds into general circulation models, then you can get a much better understanding of the atmosphere. So we have this is a diagram that sort of covers that. This is from one of the old IPCC reports. So this is where particles in the atmosphere will either scatter or absorb radiation directly. So we call that a direct effect. So, and all the other ones are indirect because these particles will affect how bright they are, the size of the cloud droplets, how long they last, the persistence, how they rain. You can affect how a cloud rains, this idea of cloud seeding, the altitude of them. So there's all these, and they're known as indirect effects. And this is the complexity, this is where the uncertainty is in the climate models, and this is what people are trying to work out at the moment. So we can think about, if we put aerosols into the atmosphere, they have a direct effect, they immediately start scattering light, but also they could produce clouds. But if we put them into the stratosphere, which is what Pinatubo did, there's a direct effect, so they start to reflect incoming solar radiation. So the question is, can we do that? Can we do our own Pinatubo? So no one's going to put TNT or a nuclear weapon into a volcano. So the idea is we put a balloon up and we squirt various different materials, sulfate aerosols, things like that, high up into the stratosphere. And a lot of these things like sulfate aerosol, it gets removed from the atmosphere relatively quickly. We've seen that from Pinatubo. We've seen that it went up into the atmosphere, and after 2 or 3 years, the Pinatubo signal was just about completely gone. Other ways of people, so this is one way, putting the balloon up, seems reasonable. Other people have suggested using F-15 fighter aircraft and even artillery to fire cannons, shells up into the atmosphere. Some of these are slightly more crazy than others. And actually, this is from a couple of weeks ago. So there's a group in America, and they're now starting to think about in the first half of next year. Lots of people have talked about it, but this is where they're really prepared to have a go and put a balloon 20 kilometres up over America, but they're only going to release 100 grams at a time, so not much. Enough to get a signal so they can measure it, and they're going to put calcium carbonate in, something that's fairly inert, into the atmosphere. And then what they'll do is the balloon will simply turn around and watch what happens with the particles. But that was announced just a couple of weeks ago. They're really going for it. Now, if you talk to some people, they think we're already geoengineering the climate by squirting things into the atmosphere. So, how many people are on social media in this room? Twitter or Facebook? No one's going to... No hands going up. No hands going up. I'm not sure about that. But certainly on Twitter, if you've got nothing better to do than fill your time, put chemtrails into Twitter, because it's like joining the Flat Earth Society and things like that. And chemtrails and with apologies to anybody who believes in chemtrails in this room, I'm guessing there's nobody. But these people really are crazy people. You know, man didn't land on the moon. The Earth is flat, all those sorts of things. So they believe that these contrails are us geoengineering the climate already. And you can't argue with them. You cannot argue with them. There's always an answer. So, back to Guinness. I'll never get round to that. So, what colour's Guinness?
Black.
What colour's the top of Guinness?
Silver.
Yeah.
No.
Well, it's not black.
That's how it works.
It's not.
But it's the same stuff, so how can that be? Well, why is the top of Guinness not the same colour as the bottom of Guinness? So, and that's simply because of the size of the droplets. So it's about scattering and mean theory and these sorts of basic physical concepts. But it's a good description because you can explain to people, Guinness is 2 different colours, and that's simply because the way you're looking at it, how it's interacting with light. And they'll understand that, and they'll remember it. Students especially will remember if you can tie something, if you can explain a physical concept by talking about alcohol. Okay? And it's not just students either. So if we can make droplets smaller, we can make them brighter, more reflective. So, but what we're not doing is we're increasing the amount of water there. We're getting the water and distributing it over smaller, more droplets that are smaller. And we get this sort of brightening effect. So we've got dark clouds and then just smaller droplets, whiter or brighter clouds. We can see that very simply here. These are all very simple experiments. You can just buy glass beads and you can show them to people at a school. You can just if you put a laser pointer in here, you will see the laser, photons escaping, but not so much here. It's exactly the same sort of thing. It's always good if you can show someone, not just explain it, but actually show them something. And you can see that here. So this is what we call ship tracks. So this is not just the smoke and exhaust that comes out of ships, and we know that because if we look at the size of the droplets, you can see that inside here the droplets are much, much smaller. So the ships are generating clouds through their exhaust. So can we simulate that ourselves? Obviously this is a very small patch of the ocean. So that's where they're producing clouds from being no clouds. But can we go somewhere where there are lots of clouds? This is off the coast of South America, where there are lots of clouds, and just take the water that's in the clouds and just chop it into smaller pieces, make the droplets smaller. So can we make these clouds brighter? And what we've got here is this is a visible satellite image, and this is an infrared satellite image, and all it's showing is the visible will show where all the clouds are, but the infrared will give you some indication of the height of them. So because these clouds are a similar colour to the ocean surface, a similar temperature, so these are low down. These are quite low over the ocean, whereas these are high cirrus clouds, and these are particularly high here, because there's a much bigger contrast to the surface underneath, so we can see that. So what we've got here is an extensive low-level cloud field. So we've got a good thing to go and have, try and do these experiments with. And ideally what you want is somewhere where the clouds are there all of the time. So this is a stratocumulus deck that forms off the coast of South America. It hardly moves around. You get the same sort of thing off the coast of Southern Africa, but it sort of moves quite a long way out into the Atlantic. And this is where the seas are fairly ferocious. The seas are some bit calmer on that side of the Pacific as well. So logistically it's a little bit easier. If you're going to have to go and work out there, the easier it is logistically, the better. So this is one solution. I quite like this, just because it's a nice sort of engineering solution. So they have these ships, and this is the idea is that these would be 200 or 300 meters long. They are powered by, now those are actually sails. They're orientated so they catch the wind. So there's, this is not a ship that's full of fuel driving around. That sort of defeats the object. And what it's doing is it's just squirting seawater into the sky. So it's no chemicals. So even if it does go wrong, these are going to produce clouds and rain out quite quickly. So from a safety perspective, it's a fairly nice, safe solution. One of the big problems is how many of these ships you'd need. I think that's one of the main problems. But this is one that I do like, because it's just, this is quite an elegant solution. But in the table, they're still saying just how effective is it, and how many ships would we need to actually build to do this. So there's again another little nice graphic here, and this just takes some of the different solutions and looks at them from the effectiveness. The effectiveness is the green at the top, and then below the safety, the readiness and the cost of these different solutions. The space reflectors, which I haven't really gone into here, huge cost to get them out there. They would work, they would be effective, they'd be out of the atmosphere, between us and the sun, but they wouldn't be expensive. And again, we go back to the CFCs or the lead in petrol. You've got to be absolutely convinced that nothing would go wrong with these. So one thing about geoengineering as well is if you're cooling the climate, how's that going to affect things that you rely on, like growing crops? So this is looking at some of the negative effects, and we got this from El Chichon and Pinatubo. And what we've got here is the drop in direct radiation impacting the surface, but the diffuse goes up because there's particles, so the light's been scattered. And if we look down this line, so that's the aerosol optical depth, stratospheric aerosol optical depth, just showing the signals here. This is the important one to look at, the 4 different colours. Each one of those colours is one of the 4 staple crops for the planet. So we've got maize, wheat, soy and rice there. And whilst El Chichon it's not completely clear that everything's dropped, because soy does see a little bit of an increase initially and then it just recovers again. But for all of them, after Pinatubo, all of them have gone down in yield. So, and that might not be, you know, a big yield for a developed country, but in Africa, Bangladesh, places like that, where they are living on the absolute poverty line, if you reduce crop yields by 5%, the implications is people just start dying. So who's prepared to undertake geoengineering as a solution for the planet when you're going to have people in Bangladesh dying? So that's something to think about. And then finally, I was just going to just quickly say about the albedo work that I've been doing. So this is the Greenland ice sheet. So the Greenland ice sheet, this pristine lump of white, beautiful ice, is not the case. So this is picture showing basically stuff that lands on the surface. So that's pollution. Traditionally, people thought it was just black carbon, industrial pollution, but now we know it's things like mineral dust, and also there's algae growing on the surface. Now, if algae is growing on the surface, that means there's a seasonal cycle because it's dark 6 months of the year. So that then if you start to want to model this, you have to start thinking of those sorts of timescales.
Is this oriented toward north, or where is the orientation?
Now I don't know that question, it's not my photograph. This is on the southwest side of Greenland, so we're seeing that here. So this is the increase in albedo, or the decrease in albedo, over 12 years from MODIS. So that's collected. So you can see that this is having an effect all up this side of Greenland. So we're doing an experiment here and then up here earlier this year. And this is one of these large projects funded by the National Environment Research Council in the UK. So it's led by people in Bristol, there's Leeds, Sheffield, Aberystwyth, and then GFZ in Potsdam. And we're looking at all sorts of different pieces of the jigsaw of this. So I'm the atmospheric scientist thinking about the input, the material landing, arriving, long-range transport onto the surface. There's glaciologists, there's people looking at remote sensing, satellite retrievals, microbiologists, geochemists. So there's, hopefully we've got everybody, or we've got someone who can, for every single part of the jigsaw piece, so to speak. In this sort of area, there's a very rapid positive feedback where if you warm the atmosphere, some ice melts. If sea ice melts, you decrease the albedo of the ocean surface because you're taking white off the top and leaving the dark surface underneath. So you've got this very rapid feedback. So once it starts, it's very difficult to slow it down. So we're seeing that. So traditionally, people thought this is all the pollution. And if you look at satellite images, you can see this stuff. The Californian fires from about a month ago, if you look at those there, a lot of those going up north, we're actually seeing that happening. But there's also this material growing, this is algae growing actually on the surface, and you can see these, and they're different colours, so they produce their own pigments. They produce sun cream, so they change colour over the season as well. So this is actually our camp. So you can see that the water courses. So this is about 1,100 metres altitude onto the Greenland ice sheet. There's a kilometre of ice below us. So, and we have a mess tent. This is the lab tent, mess tent, and then there is our sleeping tents. And these are simply features from the surface underneath that percolate up through. These are not. There's no trams or anything like that. These are bizarre, very straight lines that you see. Unnaturally straight lines compared to the water courses. This is just like a geography lesson. Seeing these, but these are basically just lines in the strata, 1 kilometre down, and that feature percolates up through the ice sheet. And in snow, people have seen this for quite a long time. So we get algae growing on the snow, green snow and red snow, and you can see clearly there's a different colour in these. This stuff melts a lot quicker than clean snow. But we get this on ice as well, so clean ice, this grey ice, and when it sort of melts, you get these kryptonite holes forming. So there's the same amount of material there as through there, but because that's so concentrated, that looks a lot darker, that melts quicker than that. And one thing about that is that only looks dark when you're looking straight down at it. So if you think about the sun shining on it, this cryoconite surfaces are very bright until the sun's directly over the top. So it's very reflective. So if that's my surface and I'm the sun going over the top, reflective, reflective, suddenly not very reflective, absorbing. So then you've got to think about this on a 24-hour cycle. You've got to put that into your model. So it's not just like an average for the year. You've got to think about that on a 24-hour cycle. So you've got to make sure you've got all this information into your models. And if we look at the surface itself, so this is something that for a long time I'd seen pictures of SEM and TEM and things like that, but now working with the geochemists, I'm actually going and using these instruments. So this is the clean snow, but it's, you know, it looks clean, but it's full of minerals. This is actually a cell. This is biology here. Even the clean ice, there's still material. These are the pores of the filters underneath. So these are actually the minerals that we're looking at in here. And the minerals, depending on what minerals they are bioavailable, so they're providing nutrients for the biology, because this is a very nutrient poor zone. Looking at different scales, so these are the protein chains, things like that forming, and then as we zoom in, we've got the minerals, and you can't see it there, but I've highlighted it there. So this is black carbon, this is soot. So we're looking at 200 nanometers now. So this is the fine particles that's come out from industrial, out the back of cars, somewhere else on the planet. You can see the change in albedo. So the important thing that we're doing from this is we need to do what's called ground truthing. We need to incorporate this biological signal into the models and not just say, oh, it's all black carbon. Because the biological signal has a 24-hour cycle, it has a seasonal cycle, so we need to increase the complexity of our models so we can answer these questions. So, and finally, so we think about Greenland, people go, oh, but no one lives in Greenland really. You know, there's 20,000 people live in Greenland, so you know, globally people don't really care that much about Greenland. It's very useful as a barometer because we can see the effects happening very quickly. But there is this concept of the third pole. So the third pole is the Himalaya, and it's the melting of the Himalaya that we can learn from Greenland, because Greenland is a simpler system. But with the Himalaya, there is 1 billion people reliant on the melting of the Himalaya. So Bangladesh, small country here, does anybody know what fraction of the world's population lives in Bangladesh? Anybody? 5%. It's huge, absolutely. For the size of it, phenomenal. How do they live there? They all stand like that. So, but they're reliant on this. But all the developing countries, you've got China and you've got India, all these burning fossil fuels, changing the colour of this, changing water courses, changing the annual cycle of the Ganges. So huge implications on that, and we are seeing, this is actually more sensitive than the rest of the planet. The poles are the most sensitive area, but the third pole is also very sensitive. So we're seeing that, and there's, this is the effect on such a huge population is just phenomenal. So it's another thing to think about. We're not just thinking about these esoteric places that only scientists go to, and they fly there in a helicopter, it looks beautiful and take fantastic photographs, and no one goes to. We're trying to help understand this as well. So finally, just to wrap up, and this is again a table, one of the key tables from this report, and it just basically breaks down the effectiveness, the affordability, the timeliness and the safety. So it shows there's a huge matrix across this. So some things are, it's like anything, good in one area, bad in another, so there's a big balancing act. So, but I do encourage you, if you are interested, do have a look at that. There are lots of, if you put geoengineering into Google, there are a lot of flat earth chemtrail type people that will tell you about geoengineering as well. So if you want, a good source of material, I would send you to the Royal Society. And then just finally to acknowledge the European Association of Geochemistry for allowing me to visit all these fantastic places. and Mariel, who organised this, and you may have noticed the noise of me moving around. So I broke my ankle 5 weeks ago, and at one point I rang her up and said I might not be able to travel. And she'd put so much time and effort into coordinating this. When you know, the doctor said I was all right to travel, I think she was happier than me. The thought of rearranging all of these. So with that, I'd like to wrap up, and I'm happy to take any questions. So thank you very much.
Thank you very much for this talk. Do we have questions, comments?
According to your opinion, which of these geoengineering techniques would be the best, the most safe for the Earth?
That's a standard question, and to me, it's none of them. It's things like putting a jacket on. We're removing carbon dioxide from the atmosphere, but we have the power to prevent, you know, if everybody puts a little bit less carbon dioxide into the atmosphere, those sorts of things. So, because, I mean...
Same as plastic and CFC,
yeah. But you see, with plastics, people say we should stop using plastics altogether, but that's wrong. Because plastics are, where they are useful, medical, you know, you can sterilise plastics, one use, you know, the number of lives that are saved because we can have sterile plastics, those sorts of things. Food, you know, keeps food fresh. So food has a longer shelf life instead of it going in the bin. You know, fruit that rots down produces all these gases. So it's just a more sensible approach. So, you know, I start to sound like I'm on some sort of missionary statement, but, you know, it's in our control. So we can back off the consumerism. You know, because you know, as scientists, we know that there are things that it's very easy to control, and everybody says, "Oh, but mine won't make a little, you know, much of a difference." And that's what it says about the geoengineering. You know, some of the, you know, we can't plant trees because it's only a small effect. But if we can get, you know, buy-in from people, then politicians start to listen. So when I was at school in the UK, there were power cuts in the 70s. So there were signs next to light switches, and it would say turn the light off. So you turn the light off. Now where I come from, you turn the light off because your dad tells you to, because it's just wasting money, but it was actually saving energy. So if you can get that sort of thing, so if you can educate children to start saying it to their parents, they're more likely to start saying these sorts of things. You know, in the UK, plastics has become a huge story, and that's down to one person, David Attenborough. So he had this television programme earlier this year. He spoke to COP24 3 days ago. He you know, on behalf of the people of the planet, you know, about, you know, that we're changing the climate. But the TV programme he had showed animals dying. You know, we've all seen the photos of albatrosses, and they open them up and they've got 25 grams. And a bird that weighs 100 grams, 25 grams in its stomach is full of plastic, and there's no room for food. But showing those on television brought it home to people. Those sorts of things. So then you get this sort of social feeling. So actually, I talk about this geoengineering, but I think, you know, we should we have some responsibility as well, because, you know, people will vote. You know, think about the politicians. Like I said, the politicians, they think about their lifetime is 4 years or however long they're elected for, you know, because they're doing a job. You know, there's not so many politicians. I'm sure they'll all say, "Oh, I'm here for the good of the population," and that's, you know, the politicians are thinking about when they'll next get elected and those sorts of things. So you've got to get this sort of ground effect, and then the politicians have to start thinking about it. But, you know, you only have to look at the way the oil industry runs a certain country on the other side of the Atlantic, you know, and you know, how quickly things change when the politicians change. So, I mean, but they make people think about it, but ultimately, you know, should we just stop or reduce, you know, reduce consuming plastic and those sorts of things?
Okay, I suggest that we have a short break, maybe 10 minutes, and then we can continue with another lecture.